Welcome everyone today to my presentation on research agents, and I'll be talking about a specific research agent called DeepSearcher that we've developed at Zilliz, which is like a very good sort of simple example that has a lot of pedagogical or teaching value. So we'll be talking about like how it works and how like even a very simple system can have excellent results. But before I start, I wanted to encourage you to, if you haven't already, check out our vector database open source Milvus, and encourage you to start the GitHub. And so typically, like at meetups, I offer swag, but because we're all virtual, I can only offer good vibes, good energy. Yeah, encourage you to check it out. So let's go next slide. Okay, so I wanted to begin with like the motivation for all of this technology, RAG, agents, semantic search. And so I wanted to mention a fact, which I think is quite like an amazing fact, something that surprised me when I heard it at first. And that is that 90% of newly generated data in 2025 will be unstructured data. And so unstructured data, of course, is text, images, sound, all of these sort of, types of data that doesn't have a readily available feature representation. So, of course, we have to put them through our deep learning neural network models to turn them into embeddings, and then we can understand them that way with that paradigm. So that's like the motivation for my company, Zilliz, as well as the technology that we work on. So we have the leading open source vector database, Milvus, as well as our commercial offerings. So before we actually get into DeepSearcher, so DeepSearcher is built on top of our open source vector database. So I wanted to just sort of tell you a bit about like what Milvus is and why I think it's really like a key piece of technology. But before we do that, I'll just give a brief introduction to myself. So my name's Stefan. I'm a developer advocate with Zilliz. So we're the company behind the open source vector database Milvus, which has since been donated to the Linux Foundation for AI and data. So as the developer advocate, I'm sort of like the bridge between developers and users. So I really love connecting with users of Milvus, anyone who's interested in vector databases, generative AI more generally. So that's my QR code to my LinkedIn. So I encourage you to connect. I'd really love to hear what you're building, and if you have any it just takes you to my LinkedIn. So I really encourage you to connect and reach out. I'd really love to hear what you're building with generative AI, whether or not it involves vector databases. I love just chatting generative AI more broadly. So hopefully hear from some of you after the session. Okay, so a bit about Milvus before we go into DeepSearcher. So as I mentioned, 90% of new data in 2025 will be unstructured data, and vector search is the way that we make sense of that data. Once we've turned our like images, sound, text into vectors, then we need some sort of like a tool to store those vectors and to enable like an effective search. And so that's where a vector database comes in, or that kind of like necessitates the vector database. So Milvus is an open source vector database. One of the first ones created around 2017 to 2019. And so it has sort of like differentiates itself from other ones by the fact that it's very, very scalable. So Milvus, like unlike many other vector databases, open sourced or closed source, it can scale to vector databases in the like tens of billions of vectors and still have like a 10 millisecond latency for query search. So vector search is the new standard. You need a vector database to do that vector search, and then with your data, with your embedding models, your vector database, you can then build these new applications like RAG, chatbots, recommender systems, as well as agents. So a vector database is like a key technology behind all of those. So as I mentioned, it's the leading open source vector database, and we can like quantify that by number of forks, Docker pulls, PyPy downloads, and GitHub stars. The most widely adopted. Okay, so for time's sake, I'm just going to skip over some of this. Okay, and I think for like one sort of like testament to the sort of like the trust people have in this open source technology is the fact that there's a lot of very big companies using it right now in real life products. So whether it's NVIDIA, IKEA, Microsoft, Intuit, they all have applications in production using Milvus to serve real traffic. Okay, so one last thing about Milvus before I go into the DeepSearcher research agent part of the talk, and that is that it has these flexible deployment options. So when you're prototyping, you obviously don't start off with 10 billion vectors. So we have a version Milvus Lite, which we'll be using in this talk, and that just you can run that in Jupyter Notebook. You can work locally and very quickly prototype. When you're ready to start like serving a bit of traffic or maybe doing some larger scale prototyping on your machine, there's Milvus standalone that runs in a Docker image. And then when you need to really scale up, so 100 million to billions of vectors, we have a fully distributed version which runs on Kubernetes. Okay, so I think, yeah, so let's now talk about DeepSearcher. So DeepSearcher, as I mentioned at the start, is a very simple research agent inspired by OpenAI's deep research. So we're like very sort of, I guess, like excited when deep research came out from OpenAI, and quite a few sort of companies were trying to make not like copycats, but sort of like clones, or trying to like emulate the performance and the output of deep research. And so we have our version called DeepSearcher, and rather than sort of like try and match the benchmarks on specific benchmarks, DeepSearcher is really just like a demonstration for teaching purposes, but the output is quite good, as we'll see. So let's talk a bit about what makes a research agent. So how is a research agent different from just like any agent? So well, I think it's sort of in the name, research. So how do you do research? Well, research is an iterative process. So these quotes I've sort of taken from the OpenAI blog post release of deep research. And so in terms of iteration, they mention things like learn to plan and execute a multi-step trajectory, backtracking and reacting to real-time information, and pivoting as needed in reaction to information encounters. So there's going to be like an aspect of iteration in the flow of this research agent. Secondly, I think search and typically web search as one of the primary tools that the agent uses. I think that's sort of seems like it's sort of part of like a reasonable definition of what is a research agent. So for OpenAI, they mention trained using end-to-end reinforcement learning on hard browsing and reasoning tasks across a range of domains, and optimized for web browsing and data analysis. And then the third one, so this is kind of connected to the first two, is the use of reasoning models specifically. So in OpenAI, in their blog, they mentioned that deep research was fine-tuned on the upcoming OpenAI, upcoming at that time, OpenAI O3 reasoning model. And it leverages reasoning to search, interpret, and analyze massive amounts of text. So we're gonna, so before we actually go into some code, we'll have a brief demo, and then I'll go through the code. I think it's really useful to look at an architectural diagram so we have like a higher level picture of what we're building. So this is like an architectural diagram for DeepSearcher. And so you can see like it works like as follows. So we have a data ingestion component. And so that will take all of our data sources. Currently, those will be sort of crawled, indexed before the query is made. But in the future, I think we're going to add some like tool usage to actually actively search the web. So your data might be internal docs like PDFs, Markdown, might be crawled web pages, as it's going to be in our case. It might be structured data, JSON, could even be streaming data. So once we've ingested the data, we've extracted the a structured representation from it, chunked that, and then embedded it, and then inserted into our vector database. Then we're ready to start doing online serving. And so just imagine that like a user comes along, they have a query. So the way that our DeepSearcher is designed, the core logic is in this loop here, from subquery to going clockwise. So the first step is, and this is just a particular design. All the different groups and companies who are trying to like create or like replicate deep research, they've had like a different design choices. This is sort of quite arbitrary, but this is how we chose to do it. So we take the user's query, we break it down into subqueries. Then those subqueries, we then put through a large language model that will route it to specific collections. So our ingested data is made up of collections from different sources. And so we can use, you could use the reasoning model, or you can have like a separate smaller LLM to help decide which, what data should for a specific subquery, what data should it be looking at, which collection? We then retrieve the relevant data from the vector database. So these are our chunks of text in our case. So ones that are similar to the subquery in question. So that's semantic search. And then once we've done that, so we've got all of the retrieved chunks for all of the subqueries. This is kind of like where the reasoning model comes in, is very important. So we ask the reasoning model, are there any knowledge gaps? So given that you've answered these questions, you've retrieved this data, do you think that there's any gaps in the knowledge that you need to fully answer the primary user's query? So that's where like having this sort of powerful reasoning model really comes into play. And then it makes the decision about, like what step to take next. So again, sort of like a characteristic of an agent is it's, at least in some part of the pipeline, is deciding which step to take. So it might say like, yes, there are gaps in my knowledge, and so I'm going to generate some new subqueries and then repeat this loop again. Or it might say, no, I think I have all of the knowledge I need to create a report. So what I'll do is I'll take all of those chunks plus the subqueries, and then with a separate prompt, synthesize all of that information together and produce the final report. So this is the particular sort of like structure or architecture we chose for our deep research clone. Oh, and maybe just like something to mention briefly. So, you can choose all. So there's many different types of reasoning models, open source and closed source. So I've done this both with DeepSeek's R1 as well as one of OpenAI's reasoning models. So this sort of like architecture is like very general. It's not specifically tied down to a particular model. Okay, so DeepSearcher is open source. You can take a look at it on the on our GitHub page. So I'll paste a link in a second, but you can go to github.com/zilliztech/DeepSearcher, or if you type in Zilliz DeepSearcher into Google, should be the first link that pops up. And so here's an example of actually running it. So we're invoking this this Python program from the command line, and the query is write a report comparing Milvus with other vector databases. Okay, so just before I go on, I see there's feel free to ask questions anytime. I think I might sort of answer questions as they come up. So looks like we've got a question here from Manmeet. So the question is, the computational cost would go X times if there are X subqueries, or it may go X times number of knowledge gaps. How are these parameters controlled? Yeah, sure. So in terms, so there's a few different sort of parameters that we've chosen to limit the computational cost. And so I think in this case, we actually say, give me like, say 5 additional subqueries. We don't say, give me as many subqueries, give me as many additional subqueries as you think is necessary. So we sort of like put a cap on the number of subqueries. I think we also put, you can put like a cap on the number of iterations. So I think it's like, it's like a Taylor series summation. Perhaps like it's more accurate the more terms you add together, but the first initial terms will be the most important, and like there'll be diminishing returns. So we both restrict the number of subqueries generated at each iteration, as well as put like a maximum cap on the number of iterations, although typically like it doesn't reach that maximum. So we've got another question from Anonymous. How are you managing the chat context from all the information retrieved? Is there a sub-research agent per search query, or is it all in a single context? Yeah, so great question. So it's all, so we compose a new prompt each time, but we include the information from the previous steps in that prompt. And we'll actually be looking, assuming I leave enough time, we'll actually look at the prompt in a second, so we'll be able to see more concretely like how that works. So, okay, so here's how like the steps of that the diagram I showed you. Here's how they play out. So the first step is to break it down into the initial subqueries. So it has subqueries like what is Milvus, what are the key features of Milvus, etc. And then starts the first iteration around that loop. So the next thing is it thinks what action to perform, and so it's going to search through the subqueries in sequence, and then decide which source to route it to. And so it has, in this case, it has 2 sources it can choose from. It's got Milvus docs, which I think is just like the Milvus documentation, which has been from the website that's been chunked and indexed, as well as what is Milvus. I think that might be like a blog post on Milvus. Okay, so it searches each of those sources, gets the document chunks, so does that second source, and then repeats this process for all of the remaining subqueries. So I'll skip over that. And I've got like, rinse and repeat. So we keep doing that until we've performed that operation for all of the subqueries. And then it needs to do this reflection step to say, are there any gaps in my knowledge? And then in this case, it says yes. So what are the performance benchmarks of Milvus compared to its competitors? So that was like a new question that the reasoning model came up with based on what it thought were gaps in the knowledge that it had procured so far from the vector database. Okay, looks like we've got another question. Oh. Okay, so question for admins. Can admins share the Gemini notes with the audience as well for each of these talks? So yeah, so I'll I think in an email I'll have the slides sent out afterwards, along with the links as well. So we've got a question from Damodar. What other parameters reasoning models will consider to answer, are there any knowledge gaps? Yeah, so I think so this is, yeah, so I think it depends on your prompt. You could put in specific sort of like heuristics or principles for it to do that, sort of considering knowledge gaps. But in our case, we just chose to give it like a very open-ended instruction. So we didn't tell it how to sort of work out what a knowledge gap was. We sort of felt like, okay, this is a reasoning model. It's been trained on web scale data. It should, it should just be able to do this. And I think it sort of is able to do that quite well. But if you wanted to, I think especially if you had like a smaller model, you could, or like a model that's not specifically trained for reasoning, you could give it a much more specific prompt where you specify like exactly how to consider like what constitutes a knowledge gap. Okay, so it goes through that cycle, does like a second iteration, and then when it reflects at the end of that second iteration, it says, okay, I think I've got all the knowledge I need. There are no knowledge gaps. Now I can generate the final answer. And so via that process, it's generated a number of subqueries as well as a number of unique document chunks. And so it takes the query, the subqueries from the 2 iterations, as well as the 21 received chunks, and puts them into a prompt and generates the report. And I'll render like Markdown for a similar output later on. But you can see, like, it gives you like a fairly well-structured, sensible-looking report. Okay, so let's look at the code now. So what I'm going to show you now in about 7 minutes is a very short notebook that implements the key steps of DeepSearcher, like that core logic for the loop, but does that without like any sort of additional layers of indirection for, say, it doesn't use like a library specifically for agents. And I think that's really useful because we can see very directly like what are the prompts, how's the model being called, and it's just like much better for pedagogical purposes. So you can open this up on your machine if you want, and you can. So that QR code is a QR code to a Colab notebook. So you can open that up. You can try it out on your machine. I'll very quickly take you through the notebook now to just explain like what it's doing. Okay, so let me. I'll just zoom in a bit to make it easier to see. Okay, so very quickly, we're going to go through how you would implement the ideas in that architectural diagram for DeepSearcher from scratch. So firstly, we have to install PyMilvus. So that's the client, the Python client to the Open Vector Database Milvus. And then we're also, I've done the step of I downloaded the entire Zilliz website and chunked and embedded it. So that's 600 megabytes in a Parquet file, very easy to open up and use. I think the data wrangling is often going to be one of the most time-consuming parts, but also one of the most important to get right. So you can just download that from Google Drive. And then, so now we can read it in and just check out the data. So I read in this Parquet file using pandas, and we see that it has 3 columns. So, except you can't see them now, I've zoomed in. So there's 3 columns. There's the text. So the text of that document chunk. There's the vector. So the vector embedding. So I used a model from Hugging Face's sentence transformer library. And it doesn't show it here, but there's also a row to the corresponding website that chunk of text came from. So this is the entire Zilliz.com website, which on a single machine with like a basic computer games graphics card, NVIDIA, I could embed all of that in, I think it was a couple of hours on a single machine. So this is something that you can very easily do. So you can build a research agent for your company's website or internal documents without having to pay for any cloud services, and within a few hours. So now we need to open the vector database and insert these chunks. So we create a client to mill this, and we open up this vector database file here. Then what we do is we create a collection. So a collection is like a table in a relational database. So we have to give it like a schema. We specify like what indexing method to use for the vector search, and then we create it. And then all we have to do is just insert these rows from the pandas table into the vector database. And then just checking that everything's right. So we've got 312,000 rows. So that's how many document chunks there are. So I think it's like 75,000 web pages, which corresponds to, in our case, 312,000 chunks. So, like a sort of, not like a small scale, but still something that you can do very, very easily in memory without like any sort of, sophisticated distributed systems. So now we'll load in the embedding model because that we use for the embedding the website, because we need to embed the query. Okay, and so the query is going to be comparison between, well, I've got comparison between Milvus and Weaviate here. I think actually the answer down the bottom, the report is something like compare, write a report comparing Milvus to its competitors. So we then search the vector database, and this is just sort of like testing it out to make sure everything works. Okay, but let's get into the actual sort of meat of the loop. We've got a couple of minutes before I'll leave a few minutes for questions at least. So our system will be prompting the reasoning model at various times for different tasks. So we'll have a query to break the query down into subqueries. We'll have a query to re-rank the chunks that are received from the vector database, retrieved from the vector database. We'll have a prompt that will summarize the chunks, the subqueries, and produce that final report. So in this case, I'm using OpenAI, but you can sort of swap that out with whatever model you want: reasoning, not reasoning, local, cloud. It's sort of agnostic to that. Okay. Oh yeah. So here's the query. So write a report comparing Milvus with other databases. So we take the query, we break it down into subqueries, and then we do the main loop. So these are the iterations. So that loop is sort of like the circle that you saw in the architectural diagram. So we encode the subqueries, we perform the semantic search, we retrieve the chunks, and then we perform this re-ranking where we ask the model to go through the chunks and filter out ones which it thinks are not actually relevant to the query. And then after that, we then reflect on any knowledge gaps. And then if it gives back additional subqueries, then we go to the next iteration. Otherwise, we then terminate the loop and we can move on to generating the report. So here's some example output here. So you can see, encoding subqueries, performing vector search. It's then sort of filtering, deciding whether to include or exclude each chunk, and then doing reflection. And then we just run the summary report on all of that retrieved data plus the subqueries. And here's the output here. So comparative report, Milvus versus other vector databases. So it has like a really nice structure, like introduction, overview. Then it goes into a bit more depth. You can see it's like producing a table, so that's nice. Going into like various different aspects, so different sections, different headers, answering different sort of I think they might sort of like correspond to the sub questions that are broken down into. Not exactly one-to-one, but it's using that sort of like decomposition to break to structure the report. And then also has a number of useful contacts and references at the bottom. So I think from something that was put together in a few hours, I think I would call this a success. And this is something that you can check out the notebook and you can try this at home. You can try it on your data, and you can also encourage you to sort of like experiment with it, add in additional. You might want to sort of like change the execution flow. You could add in things like maybe you want to sort of add web search as a tool call. That could be really interesting. You might want to like make all your tool calls actually like Python code in the sandbox. There's lots of like interesting directions that you could take the code from here. But this kind of like illustrates like the very core ideas of how you can construct a search agent. So I think that takes us up to time. So let me just go back to the slides. Yeah, so where to from here? So I think there's a number of like challenges with building these research agents. So many of them not specific to research agents, but just generative AI applications in general. So the first is obtaining the data. So how are we going to get high quality open source data, especially like for training? If you want to actually train these reasoning models, where will you get those high quality reasoning traces? And then there's the cost, both for the hardware. So the cost. So these research agents make a lot of calls to the reasoning model, and so that can get very expensive very quickly. So how are we going to bring down that cost? Maybe we could be using specialized hardware like Nova, special chips for transformer architectures. Maybe we could actually replace some of those steps of the pipeline with smaller LLMs. So maybe the reasoning model is only particularly valuable at that reflection step. And then there's the scaling, just sort of like more broadly. So how are we going to scale this to both be able to search a lot of ingested data plus serve web traffic? And so that's where like Milvus and Zilliz really, I think, are advantageous. So Milvus, as I mentioned, scales to the tens of billions of vectors with sub 10 millisecond latency. But if you don't want to manage a vector database solution yourself, also worth mentioning, we have a fully managed service, Zilliz Cloud, as well as a bring your own cloud version if you have some concern or some like restrictions about like data security or privacy. So I'm going to finish up there, and looks like well, I think we've come up to time, but maybe we could leave it like a minute or two for questions. So last thing I want to mention was, if you are a Milvus user or you become a Milvus user and you want some support, you're not sure like how to, like you're having some technical challenges productionizing your application, we offer a free weekly office hours one-on-one session where you can get connected with a Milvus engineer and a developer advocate. So there's the QR code, really great resource to help get your what you're trying to build into production. So with that, I shall wrap up and turn it over to the admin team. Do we have like a minute or two for questions?
Yes, Stefan, for us here. Hey, yes, we do have some time for questions. So if you want to just click on the tile icon on the bottom right, there is a Q&A tab, and we've got a bunch of questions in there.
Okay, so I think I was trying to answer them as I go. So I think we're up to Shalini's question: is this code on GitHub for us to try? So yes, it is, and the link will be in the slides sent out afterwards. But let me just navigate to it now. Actually, yeah. So go to github.com/zilliztech/deep-searcher, and so that's like the code to DeepSearcher itself. The code to this notebook, it'll be within the slides, and I'll try and send it out as a link by email afterwards. Okay, so Anonymous, can you show what those subqueries, what subqueries are produced? So yes, let's see. Yeah, so in this case, these are the initial subqueries here. So you can see that when you open up the notebook on your local machine. And then it generates an additional 3. So these are the additional subqueries on the second iteration. And then in this case, it terminates after that. So 7 subqueries in total. Does anyone have any other questions before we finish up? Okay, well, thanks for attending my session, and hopefully you learned something. Hopefully you're inspired to try and build your own research agent. I mean, this is the very basics. I think generative AI is really something that you learn from doing and building. So yeah, hope you can take our code, extend it, build it, and then let us know what cool stuff you've done. We'd be really happy to feature it on our blog, socials, and hope to hear from you in the future. Thanks, everyone.
Thank you so much, Stefan. Thanks, everyone.